Hello everybody, this is the first video for chapter 2 material. First video out of 2, so I'll be doing 2 videos for this chapter. So chapter 2 has the following purpose. First, we're going to introduce a very simple prediction method that we can use in statistical learning. So we'll see many methods throughout the course, but we'll start with a very simple or basic one to uh, explain additional concepts which are associated to model selection. So we will discuss in-sample versus out-of-sample performance. And this topic will be very important to do a sound selection of model when we decide on statistical learning models to be used to do some statistical analysis. So this chapter discusses parts of chapters 2 and 5 from the ISL textbook, the introduction textbook, and also parts of chapter 2 from the more advanced textbook elements of statistical learning. So I forgot to say the very simple method we're going to introduce is called the k nearest neighbors method. Okay, so let's recall the regression setting we've briefly mentioned in chapter 1. So in a regression problem, we often have a data set with n observations. So yi and xi are respectively the response and explanatory variables associated to observation I, where I goes from 1 to n, and n is the total number of observations in the data set. And here, xi, the response, it can be a vector. It's not necessarily one-dimensional, so there might be many explanatory variables for each observation. And right now, we're going to consider a setting where the response y is quantitative. Okay, so we're going to assume that we're in a regression setting, not in a classification setting. So y is a number. So our regression problem will be to try to predict the response y0 of a new observation not in the original data set based on the value of its predictors x0. Okay, so we have a data set of responses and predictors, which we both have, but now let's assume that there's a new observation not in the data for which we know the predictors, and then based on these predictors, we're trying to predict the associated response y0. Okay, so this is a regression setting where we are trying to make prediction. Okay, so for this purpose, we will simulate a very simple data set to be used in subsequent explanations that we will see. Okay, so I simulated with the software R. So see this file that I've provided on Moodle, the chapter 2 regression model.r. This is the file that was used to generate this data set. So I generated a simple data set based on the following. So I've simulated first xi. So let's assume that there's a single predictor here for each response. So the dimension of the predictor data set is 1. Okay, so p is equal to 1. For each observation, there's a single predictive variable, okay, or explanatory variable. And so to make the simulation xi, I simulated from a uniform -2 to 2 distribution. I've simulated epsilons I from I goes from 1 to n, which are as IID normal 0, 1. And then the responses were simulated by applying the following. So to each explanatory variable, the function f was applied, where f is x cubed plus a noise term. Okay, so basically in this model, the response is the predictor cube plus some noise. And 60 data points were simulated. Okay, so this is the illustration of the simulated data set. The predictor x, as we said, it's simulated uniformly between -2 and 2. And then the response is the x cubed function plus some noise terms. So let's recall I'll draw a quick picture. The x cubed function looks like whoops, it's not very nice drawing, but here it looks like this, and here maybe it should be more a bit like this. Okay, so the function x cubed looks pretty much like this. So we can see that the observations follow the shape, but they're not exactly on the line because of the noise that was added. Okay, so the each data points are noisy observation from the x cubed function. Okay. So let's say this is our data set. Now let's assume that we have a new observation for which we know the predictors. Maybe the predictor is something like -0.5. And we'd like to know for that new observation, if the predictor is here, what should be the predicted value of the response. Okay, so in practice, we don't know that the true function is x cubed. Okay, so this it's unknown to us, so we cannot say we are just going to use the predictor cube. We don't know that the true function f is x cubed. This is what we're trying to learn. Okay, so most likely any sound algorithm would make a prediction maybe here, something like that. The response should be approximately, so here it's maybe just below 0 or something like that. But so this is intuitively, but then we must come up with formal way to come up with a predicted value. Okay. So the first method we're going to propose to make that prediction is called the k nearest neighbors method for regression. And k nearest neighbors, it's often referred to as KNN. Okay, so KNN means k nearest neighbors. So to explain the methodology, first let's introduce some notation. So here, let's introduce the L2 norm. The L2 norm of a vector x is given by the following. It's the square root of the sum of across all dimensions of the vector of the element j in the vector squared. Okay, so this is the Cartesian distance between the vector x and the vector 0. Okay, so this defines what we call the L2 norm of a vector. And the idea in the k nearest neighbors is this norm will be used to define a notion of distance. Okay, so the idea in k nearest neighbors is the following. Let's say we're trying to predict the response of a new observation whose predictors are x0. Then what we will do, we will go through our data set and look at all the observations and then try to find out which observations had a predictor which looked pretty much like the predictor of the new observation we're trying to predict. Okay, so then if we looked at observations which had similar predictors than the observation we're trying to predict, then the response of the new observation should be roughly similar to the response of these observations which had similar predictors. Okay, so this is the idea we're going to use here. Okay, so to predict a new observation, let's go through our existing data set, find observations for which the predictors looks pretty much like the predictor of the new observation, and then use these observations in the data to come up with a prediction of the response. Okay, so more precisely, in the k nearest neighbors method, we're trying to find the k data points, capital K data points, within the training set, within our data set, whose predictors x are the closest to x0. So this is the predictor of the new observation. And by closest, we mean which have the smallest L2 distance between x0 and x. So between the predictors of the new observations and observation and the predictor of the observation in the data set. Okay, so for each data point in the data set, we calculate the L2 distance. So L2 distance is simply the Cartesian norm between the point x and x0. So we calculate the L2 distance between the predictor of each observation and the predictor of the new observation. And then among all observation, we pick up the k observations for which the distance, the L2 distance between the predictor of the new observation and the predictor of the observation in the data set is the smallest. Okay, in the unlikely case where there's a tie, let's say there are a few observations which have equal distance, where, well, we can pick randomly observations for which there's a tie, or we can include all of them, or it doesn't matter. Let's disregard this case for the example. Let's assume that there are exactly k observations for which the predictors are the closest to x0. So the set of all these data points for which the predictors are pretty similar to the new observation predictor, we denote it by this stylized n, so n0k. So n means the set of neighbors, k means that there are k neighbors in that set, and 0 means that this is the neighbors for the new data point x0. So neighbors means value observations for which the predictors are similar to the one in x0 in the new observation x0. Okay, so then how do we come up with a prediction in the K&N method? The predicted value for an observation, so here this should be y0, so y, sorry for that, maybe I should have put a 0 here. The predicted value for a new observation y0, whose explanatory variables, so here there should be no s here because there's a single variable in our case, or there should be r instead. So let's start again. The predicted value for an observation y0, whose explanatory variables are x0, is the average of the response for the neighbor's value. Okay, so our prediction y hat for the new response is simply 1 over k, so times the sum across all observations in the neighborhood set. So this is an average of yi, so yi is the response for the ith neighbor in this set. Okay, so basically what we do here, we take all the k nearest neighbors for our new observations, which were observations whose predictors were most similar to the predictor of the new observation. And then for all these neighbors, we average their response and we assume that this should be the predicted value for our new observations. Okay, so the underlying lesson here is that if the response, if the predictors for several observations are similar, then their response should also be similar. So let's take the average of the response of similar observations, and this should be a good approximation of the response for the new observation. Okay. So let's do this. Let's give an example. So here I've plotted again the simulated data set, and then we can do the following. So let's say we have a new observation at x0 is minus 0.5. So here this is x minus 0.5. We'd like to come up with a prediction of the response. So we'd like to know where on this red line should we put a dot to make the proper prediction for the response. So to do that, what we'll apply here is the k nearest neighbors with k is equal to 4. So The example k is equal to 4 is provided, but in a few slides we'll discuss how a suitable value for k should be chosen. Okay, but for now let's assume k is equal to 4. Let's not consider other values. Let's just illustrate the method for an arbitrary value of k is equal to 4. Okay, so when k is equal to 4, we look the predictor here, and we're trying to find which are the values or the data points whose predictors are the most similar to minus 0.5. And here I've put a plus sign or a cross sign on such observation. So the 4 points whose x value is closest to minus 0.5 here are this one here, this one, and this one. Okay, so these are the 4 points for which the x is closest to minus 0.5. So then what we do to make the prediction, we just average the response of these 4 observations. And if we calculate the average, then the average is the average of the y of these 4 values is equal to this value. So here, this entails making that prediction for the response. Okay, so this method, it's pretty intuitive. For a new observation, we just pick the few observations whose predictors are the closest to the one being the predictor of the new observation, and then average the response. And this is illustrating how we do that. Okay. So in the previous method, we've illustrated how to get the prediction for a single value of x, but we can repeat this approach for all possible values of x. Okay, so here the plot illustrates the predicted value for a k-n method with k is equal to 3. Okay, so last slide we used 4, but now let's use 3. And then for all the x's, we can repeat the procedure followed previously to come up with the prediction. And the blue line here illustrates the prediction that would be made by this k-n method for all values of x. So right away we see that the behavior of this method is not very smooth, because as soon as you move a bit, sometimes the nearest neighbor changes abruptly. So the predictions are not very smooth and change abruptly in this case also. Okay. So is this a good prediction method? Well, yes and no. So yes, it somewhat follows the correct trend, but no, because it varies very non-smoothly, and maybe we should have prediction methods which behave more smoothly. Okay, but for now, let's assume that this is the method we use. Okay, so these are predictions for all x's when k is equal to 3. Now, what is the effect of k? So we might be wondering, well, what if we change k from 3 to 4 to 5 to 6 to 10, or from 3 to 2 to 1? What should be the effect of this? So here, the plot provides the curve for the k nearest neighbors with k is equal to 1, and the k nearest neighbors for k is equal to 10. Okay, so let's study first what happens when k is equal to 1. We can see that we do a 1 nearest neighbor. So every time we make a prediction, we take the single closest observation to make the prediction. And when we average the response, since there's a single prediction, there's a single neighbor, the average is simply the single value of the response for that neighbor. Okay, so here, this is why we see in this region, the nearest neighbor is this guy, so the prediction is exactly its response. So here, when we become closest to this guy, the prediction suddenly jumps to the value of this guy, etc., until here, as soon as we cross that point, then the nearest neighbor becomes this guy, so the prediction shrinks right away. So we see that when k is very small, the prediction curve becomes very bumpy to exactly pass through the response of each observation. Okay, so here we see that the prediction kind of picks up the noise of each observation and goes through exactly all points. So in a sense, there's a perfect fit, but the prediction becomes extremely bumpy and very sensitive to the noise because the prediction incorporates the noise within the data set. Okay, conversely, if k is very large, then the opposite happens. Okay, so when k is very large, let's say at this point, instead of having one neighbor, we consider 10 neighbors. So a whole bunch of points, and then average their response to come up with the prediction. So because many more observations are taken into account, the prediction varies much more smoothly. Okay, so for example, when we move across the x-axis, at some point, out of the 10 neighbors, there's only one of the 10 that switches. So the averages, they vary more slowly because instead of changing the single neighbor every time we move along the x-axis, it's only one neighbor out of the 10 which is changed. So the average doesn't change much every time we go through the x-axis. But we can see that here it varies more smoothly, but it's somewhat underreact. So for example, when we're in the tail here close to 2, when we're averaging 10 observations, we don't only average these ones, but we also average observations that are somewhat far away and are not necessarily relevant because their predictor being too far away, their response should be not that similar to the one here. Okay, so we can see that here in the extreme part of the x-axis, then having too large of a k underreacts because it has to average observations that are too far away and somewhat irrelevant. Okay, so let's summarize this. So the larger k is, the less sensitive predictions are to variations in observed data. Okay, so for large k, let's say k is equal to 10, if we just change one data point, the predictions won't change much because the response for that observation we're changing its average across responses from 10 observations when making predictions. So the weight of this observation will not be large when making predictions. So when k is large, predictions are not very sensitive to the observations, or are less sensitive. Conversely, when k is small, the average contains only a few observations, and then changing one observation can drastically change the predicted values for some value of x. So in a sense, when k is too small, the model is too flexible because, as we saw, the curve is very bumpy and it captures the noise instead of capturing the genuine x cube pattern. Okay, so the curve fluctuates like this not because it follows the pattern, but because it follows the noise of observation. And this phenomenon, it's known as overfitting. So overfitting means that your prediction approach captures not only the true pattern but captures the noise. And this is undesirable because, of course, what you're trying to find when you make a prediction, you're trying to find the pattern. You're trying to disregard the noise associated to observations because the noise, of course, is idiosyncratic to each observation and will not help you predict values for new observations. Conversely, when k is too large, the model is too insensitive, and we say that it's underfitting because it cannot replicate the pattern. Okay, so let's go back here. So let's maybe draw in blue. The true pattern, if we draw it in blue here, it looked like something like this. Okay, so we can see that the green line here, we said it was too insensitive and it doesn't react enough to increase of observations at the extreme part. So we don't, here on this part we have an inaccurate representation of the true pattern, and this is known as underfitting. So underfitting means that your model is inaccurate because it doesn't react properly to observations from your data set. Okay, so you are unable to replicate the pattern. So now the question that emerges from this is, how can we determine a suitable value for k? Okay, so we said k too small, it's bad because it overfits, it's too sensitive. K too large, it's bad also because it's underfitting and it's not sensitive enough. So there's probably some optimal trade-off to choose k, which just gives the proper amount of flexibility to come up with the best possible predictions. Okay, so how do we identify the k which provides that best trade-off and give best predictions? Okay, so of course, then there are many ways we can do that, but what we will propose here is one, let's say, standard approach followed by many people in the literature and practice. So to do that, we must first introduce some like measurement approach to assess the quality of the fit or the quality of predictions made by our model. So to assess the quality of predictions made for any given value of capital K, so any value for the number of neighbors considered in predictions, we must have some criterion to evaluate the quality of the fit. And in a regression setting, so if you've done linear regression, you should be well aware of this criterion. The most commonly used measure is the mean square error. Okay, so the mean square error entails averaging across all observations from your training set the square difference between the response of your observation minus the predicted value based on your model for that observation. Okay, and you square that difference. So mean square error, it's the average of the squared error. So the error is the prediction error, your true response minus your prediction squared. So this is, so in linear regression, this is known as a least squares approach. Okay, you're trying to find predictions which reduce the MSE. So here, notice that in this case, I goes from 1 to n. They refer to all observations within our data set. Okay, so to assess the quality of the fit, we look at our observations in the data set in the standard MSE criterion. Now, the smallest the mean square error, the better the model fits the data in your data set. Okay, so if you have a very small MSE, it means your predictions closely match the responses in your data set. Okay, so as we said in the previous metric, the previous slide, the criterion we considered involve computing the prediction errors on the same data that we used to train the model or determine predictions. Okay, so we made predictions based on one model, based on one data set, which was the simulated data set, and then this criterion here, the MSE, is calculated by looking at all observations from that same data set we used to make prediction and check their errors. Okay, so this quantity is known as the training mean square error or end sample mean square error. Okay, so here we might think that, okay, perhaps we should take the value of capital K, which minimizes the training MSE. Okay, so the mean square error in our training set. Well, that clearly wouldn't be appropriate. Okay, so if you did that, then the answer would be obvious. You'd always select K is equal to 1, because K is equal to 1, the very bumpy curve here, it it passes exactly through all your data point, and your in-sample MSE would be exactly 0. Okay, so if you did that, this approach would always suggest selecting K is equal to 1, the very bumpy curve, but that wouldn't be appropriate because these predictions would always incorporate noise and lead to overfitting. Okay, so we need another approach than to minimize the MSE in the training set. So in general, what's the issue with taking the smallest in-sample MSE? The issue is, in practice, we're not interested in how well the method works on the training data, but what we're really interested in is how well will our predictions work for new data, okay, that we're trying to predict. Okay, so in practice, the values in the data set, we already know them. We're not trying to predict these. We're trying to predict new observations that were not part of the original data set. So we should design a criterion which reflects this objective, which is to determine how well does the prediction do on new observations unseen previously in the data set that was used to train the data. So, okay, so let's suppose that, as we did earlier, we use our original data set called the training set, yi and xi, I goes from 1 to n, to get our predictions, and the predictions are denoted here by f hat. So f hat is that curve, like the either green, red, or blue curve I've illustrated earlier, where you have the prediction for all values of x. This curve here represents the prediction function, which will denote f hat here. So now, since we're interested in assessing the prediction performance on new on-scene observation, what we shall do here is to consider a new data set, a novel data set of observations not included in the original data set. Okay, so what we will do here, we will denote by y0u, x0u, where u goes from 1 to capital U, being a new data set of responses and predictors which are not included in the original data set. So here, what we would like to do here is to select the value of k for which the MSE is the smallest, not in the original training set, which gave the predictions, but rather on this new data set, which we call the validation set. Okay, so we here design a new metric, which is the average of the response minus the prediction made on the new data set squared. Okay, so this is an MSE, but over all observations of the new data set. Okay, so here the response y and the predictor x y0 and the predictor x0, these are from the new data set, but what enters the part which comes from the original training set here is the f hat. So the function f hat, it's the one that is estimated from the original data set, but then we apply this f hat on new observations and then calculate the MSE. And this really assesses the predictive ability of your prediction model on new observations you haven't seen earlier. So if you do that, what happens? Okay, so So what happens, let's say if you take a very small k, or okay, let's start with a very large k. What's going to happen? So we said that when we train the model for large k, the model is insufficiently flexible and does not react sufficiently. So it provides some underfitting to the data. Well, what's going to happen when we apply the predictions to the new data set? Still, the pattern is not captured uh, well. So predictions for the new data set will be bad because the prediction pattern that was estimated, it was badly estimated. Okay, so the bad estimation of the pattern, because it's not flexible enough, will do poorly on new observations, so the validation MSE will be very large. Okay, so that is pretty clear. So if your model is insufficiently flexible, so when you take k very large, then you shall do badly on new observation. Okay, and your validation MSE will be large. Conversely, what happens when your model is too flexible? So we saw that when your model is too flexible, such as k is equal to 1, the curve was very bumpy. So in the training data set, you will do extremely well because your training MSE will be 0. But now when you try to predict for the new observations that weren't seen, well, then all these bumps in the prediction model, they will not help your prediction, but they will harm your prediction in the new data set, because the noise in the new data set will be different than the noise in the training set. So it doesn't make sense to use the noise in the training set to predict the noise in the validation set. So because of that, the very bumpy aspect of the curve incorporating the noise will harm your predictions in the new validation set, and thus you will also do poorly by having a large validation MSE. Okay, so we see that contrarily to the training set, which led to smallest MSEs when k is very small, for the validation set, the validation MSE will be very large is if k is very small or k is very large. Okay, so using a validation MSE encourages to find the suitable sweet spot trade-off to come up with the best possible predictions for unseen data. Okay, so the proper trade-off is determined by minimizing validation errors, which are prediction errors made on the new data set called the validation set. Okay, so for the purpose of illustration of this approach, a new data set, so we've simulated the original data set, so x cubed plus some noise, but then what we'll do here, we simulate a novel data set, which still is x cubed plus some noise, but now the noise is not the same than in the original data set because we've simulated new observations. Okay, so the x's and the epsilons in the new data set are different than from the original data set, and of course, because of this, their responses are also different. Okay, so we have two data sets simulated from the same model, so x cubed plus noise, and we use the first original data set to train the model, so to come up with the prediction functions f hat, and then we use these f hats on the new data set to come up with predictions, and then we're going to look at validation MSEs for on this new data set. Okay, so here, as a nutshell, the model only uses the first training data set responses to make predictions. Okay, so no responses from the new data set are made to are used to make the prediction. So it's really unseen. So when we make the prediction errors, it's really a genuine representation of the reality where you cannot use the response from the new data set within the prediction. Okay, so the prediction does not rely on the response of the new data set. Okay, so the training MSE, as we said, it's the MSE based on all observations of the original data set for which the responses were used to come up with predictions, whereas the validation MSE measures errors on on-scene observations where the training of the model did not rely on these new observations of the validation set. So here is the plot of the evolution of the training MSE and validation MSE for all values of k. So here we see exactly what we discussed earlier. So if we take the blue dots, so here the x-axis is all possible values of capital K, the all possible number of nearest neighbors, and we can see that the smallest value of k leads to the smallest possible error with exactly no error, so an error of 0, MSE of 0, when k is equal to 1. So this is exactly as we said. When the model becomes very, very flexible, in your original data set, you don't make any error anymore because the curve matches exactly all observations in the original data set. But now, when we take the validation MSE instead, what happens is that the curve decreases and then starts increasing at some point here. So when you have super large k, we said that there's underfitting and you have bad MSE for the validation set. And when k is too small, then your model is too flexible. So although in your training set you don't make any error, when you consider new unseen observations, you make larger errors because your bumpy curve, the bumps in the curve are harmful to make predictions on new observations. So we can see that when we look at the validation MSE, there's some sweet spot here. So some value of k which reduces the validation MSE, which is the accuracy, so the errors you make on new unseen observations. So the approach we propose to follow here is to select k, which minimizes the MSE for a new unseen observation, which genuinely measure what you're interested in practice, which is the accuracy of your predictions for new unseen observations. Okay, so we can see that this method allows us to determine the suitable degree of flexibility of the model or suitable value of k to make predictions. And you don't come up with always it's the smallest k. No, there's a sweet spot which gives the optimal trade-off of flexibility of your model to avoid both underfitting and overfitting. Okay, so in that example we've showed the optimal value was k is equal to 3. So here k is equal to 3. 3 is the value which minimizes the validation MSE. Yes, that's it. Okay, so here this is just repeating what I just said, but the pattern observed in this plot, it's we've presented it for a single problem, but it's very typical of all or many regression problems we observe in practice. Whereas as the flexibility of the model increases, so in our case it means k decreases, the training performance always improves. Okay, because the very flexible model, they'll go exactly through all your points of your training data. So it looks, if you just look at the training set performances, it looks like as if the performance is perfect because you match exactly all the points. But this is clearly overfitting. Okay, so in the training set, as you increase the flexibility, the training performance always improve, so the MSE decreases. But however, past some point, The decrease in MSE in the training set is simply due to overfitting, so to fitting the observations and the training data too well. So at that point, although the training error will continue decreasing, the validation error will start increasing, because when we do overfitting and we pass exactly through all the point, then at this point the excessive flexibility we obtain leads to overfitting, so the predictions tend to worsen up when we consider new unseen observations. Okay, so there's an optimal level of flexibility you want to have if you don't want to overfit and you don't want your validation errors to start increasing. Okay, so one last analysis we shall explain is to try to illustrate what we've discussed intuitively with more formal mathematics. Okay, so here we've talked about the MSE, mean square error, for the validation set, which we said we should try to find the K or the flexibility which minimizes the mean square error. But now let's look at this mean square error and let's try to decompose it to see what happens a bit better. Okay, so here the decomposition we're going to illustrate is called the bias-variance decomposition of the mean square error. Okay. So what happens here, let's say we have y0, some observation of the validation set associated with its explanatory variables x0, and just for simplicity, let's assume that in our calculations x0 is deterministic. Okay, so in the previous example we've simulated them randomly, but let's not go into this. Let's just assume x0 is a given fixed value to make explanations more simple. Then, in that case, the mean square error or expected square error, sorry, I'll use expected square error here, for the new observation can be decomposed into three main sources, as we'll show next. Okay, so the expected square error between the response of the new observation and its prediction based on the predictors of the new observation and the estimation function obtained from the training set can be written as this. So we can replace the response by f of x0 plus epsilon. So this was our assumption, regression model assumption. We assume that the response is function f reflecting the pattern, or also this is called the signal function plus some noise term. And then we can expand that square. So this here we can regroup f of x0 and f hat of x0. So this is the expectation of this squared plus the expectation of epsilon squared plus the cross term here. So twice times the expectation of epsilon times this. Now we have to notice, so here this term here, it will be equal to 0. It vanishes. And why is that the case? Well, it's because here epsilon is the noise term for the new observation in the validation set. So the noise for this new observation is independent from the right side, where here, because we assume x0 is deterministic, this is a deterministic quantity. And here, this is not deterministic because f hat is random, because it depends on random observations from the training set. But the randomness, as we just said, the randomness of f hat is related to observations in the training set, because it's the training set observations who provided the predictions. Okay, so this randomness depends on randomness associated with training set observations, whereas epsilon depends on the randomness associated with the validation set. And both the training set and validation set, they are assumed to be independent. So we've simulated from two data sets independently. And in practice, in what we will do, this is this will be our assumption that if we have two data sets, a training set and a validation set, both should be independent. So if that's the case, then this epsilon is independent from this. So the expectation can be broken down into the product of the expectation of this times the expectation of this, and the expectation of epsilon is simply 0, so this term vanishes. Just a quick digression here. In the class here, we're going to assume that the training set and the validation set are independent, but in some fields, it's very hard to have something like that. So I personally, I'm from finance, and often in finance there are correlations all over the place. So if you take what happens in a given month, there will be dependence with what happens in another subsequent month, for example. So it's not very easy to obtain independent data sets. But this is nevertheless the assumption we'll make for the current class. If you want to generalize for or see how to correct for dependence between the training set and validation set, there are more advanced methods for that, but this is left out of scope of the current class. Okay, so here, current class, we assume training set, validation sets are two independent data sets. So in that case, we see that the expected squared error for the new observation, okay, whereas the response of the new observation minus its prediction, it's equal to the sum of two terms because the third term vanishes here. And this is the expectation of the noise squared, which is the variance. So because the noise term epsilon has an expected value of 0, this is the variance of the noise plus something here, which is the expectation of f of x0. So the true pattern function associated with x0 minus its prediction. Okay, so here we take that, copy paste it, and saw that the second term, expectation of epsilon squared, was the variance of epsilon. And then we have the following relationship: expectation of x squared, is always equal to the variance of x plus the expectation of x squared. Okay, so this is what we do here. The expectation of this squared is equal to the variance of this plus the expectation of this guy squared. And here, because f of x0, as we assume x0 is deterministic, f of x0 is constant. So when we calculate the variance, we can remove the constant here, so this becomes the variance of f hat x0. Okay, so here our expected square prediction error is the sum of three terms, the variance of our prediction. Okay, so this is prediction variance or estimator variance, plus here this is the squared value of what we call the bias. So the bias is the true value of the expectation of the response variable for the new observation, and this is the estimated value this is the prediction. Okay, so here this is called the bias because it's the true expected value minus your estimation. Okay, so this is called bias, plus the last term is the irreducible error. Okay, the variance of the noise. Okay, which we said this last term, regardless of what prediction method you will use, you cannot act on this one. This will always remain there. So you cannot do anything about this. So in our previous example, when we had to choose some value for k, this impacted not the third term, but the first and the second term. So we can see here what happened. When k was very small, the model was very flexible. Okay, so it was able to go through each observation. Okay, so for this reason, when k was super small, when your model is super flexible, then you don't have bias because your model is flexible enough to match any pattern you want. So the bias is very low. but we saw that the predictions were very sensitive to observations. Okay, so because it passed through all observations, if you just moved one observation, you would completely have you would have completely different predictions for some value of x. So we see that the variance of the predictions would be very large when k is small. So this is why when you have too much flexibility, your validation MSE is very large because you have very large prediction variance, and this first term becomes very large. Conversely, so k is small or too much flexibility, this is very large, this is very small. Conversely, if you have large k, so very low flexibility, then your predictions are pretty insensitive to observations. So this variance is small because changing one observation will not alter much your predictions. But because you're underfitting, so you don't have enough flexibility, you're unable to represent the correct pattern underlying the data, then this bias will be very large. Okay, so K is very large, or insufficient flexibility means this is small, but this is very large. Okay, so we can see that to find the optimal K is kind of a balancing act where you don't want any of these two terms to be too large, so you want to find the suitable K which keeps both these two terms at reasonable level, so both variance of predictions and biased. Okay, so this is simply repeating what I just said in words, so I'll let you read it on your own, but it's exactly what I just explained. Okay, so in a nutshell, the conclusion is when you select the proper amount of flexibility in the prediction model, the flexibility should be increased as long as the reduction in bias you obtain by having more flexibility is larger than the increase of estimator variance. So at the point where if you increase variance more than the optimal level, if you increase the flexibility more than its optimal level, then at some point the variance will increase more than the reduction in bias you obtain, and then you start having worse validation MSEs, which is undesirable. Okay, so here we'll stop at this point and continue chapter 2 in the next video. So have a nice day and take care.